Look at a block of iron. It sits there, heavy, quiet, completely motionless. To our senses, it is the definition of dead, rigid matter. Early scientific thinkers suspected our senses were lying. In the early 19th century, John Dalton studied how elements combined and proposed that matter was composed of discrete atoms rather than being a continuous solid mass. Decades later, physicist Richard Feynman distilled the modern reality. All things are made of atoms. They are tiny particles in a state of perpetual, restless motion, pulling at each other from a distance, but violently repelling if squeezed too close. This atomic reality creates a mechanical paradox. If a solid metal block is actually a chaotic swarm of repelling particles, why doesn't it simply drift apart like a cloud of smoke? We also have a thermal paradox. When you hold a flame to that iron block, you pump thermal energy into it. If the atoms are locked deeply in place to hold that rigid shape, where does the added energy actually go? To understand how a solid hides its heat, we have to completely abandon our macroscopic perspective and dive into the microscopic architecture holding it together. Metal atoms form a structured lattice. Unlike free gas, these trapped atoms are tethered by electromagnetic forces, acting like stiff springs, vibrating violently around a fixed position. To understand their energy, we isolate one atom's movement along its single axis. As the atom oscillates back and forth along this line, it has velocity. That means it carries kinetic energy, the energy of physical motion. It is also fighting those electromagnetic springs. At the extreme ends of its swing, the bonds stretch and compress, storing energy as potential energy before snapping the atom back towards the center. This brings us to a strict rule called the law of equipartition of energy. It dictates that whatever thermal energy is available to a system, it gets distributed perfectly equally among all the possible modes of movement. A single atom oscillating along a single line holds exactly 2 equal shares of thermal energy. 1 share is kinetic and 1 share is potential. Real atoms exist in 3 spatial dimensions. Our trapped atom vibrates erratically within a spherical volume, bouncing against invisible springs on the x, y, and z axes. This creates 3 kinetic and 3 potential dimensions, giving 6 total energy modes. According to the equipartition law, every single degree of freedom holds exactly 1/2 kBt. T is absolute temperature, and Kb is the Boltzmann constant, linking temperature to molecular energy. Multiplying 6 modes by 1/2 kBt simplifies the math. The total average thermal energy for a single solid atom is exactly 3 kBt. Temperature in a solid specifically quantifies the intensity of this 6-part microscopic vibration. We can take this microscopic calculation and scale it up to something we can measure in a lab. Instead of 1 atom, let's look at exactly 1 mole of the solid, a macroscopic chunk you can actually hold. A mole contains a specific massive amount of atoms, known as Avogadro's number. By multiplying the energy of our single atom by Avogadro's number, our microscopic constants merge into a macroscopic constant. This equation shows how the math transforms. Our microscopic calculation multiplies by Avogadro's number, which leaves us with a new macro equation. The total internal energy, U, equals 3RT, where R is the universal gas constant. When you heat a gas, it expands rapidly, spending some of your energy to push outward. A solid, however, barely expands at all. Because its volume is essentially fixed, almost 100% of the heat you add goes directly into feeding those internal atomic vibrations. Since all the heat feeds the vibrations, we can define the molar specific heat capacity, represented by C. This is the exact amount of heat required to raise the temperature of 1 mole of our solid by 1 Kelvin. Based on our volume constraint, the math simplifies completely to just 3 times the gas constant, R. This chart shows the empirical proof of that derivation. The horizontal line represents our theoretical threshold of 3R, which is about 25 joules per mole Kelvin. Notice how the actual measured values for completely different elements, aluminum, gold, iron, and lead, line up precisely along that exact mathematical prediction. A heavy metal block appears perfectly static and lifeless, yet because its atoms are trapped in a uniform grid, the way it absorbs and stores heat is dictated entirely by the precise, invisible geometry of atomic vibration.